So this problem illustrates what the common ion effect will do to percent ionization. So we have a 0.0075 molar butanoic acid solution, and we should be able to calculate the percent ionization pretty easy from that, and there's other examples which I've done. And then what happens if we make this solution the same solution, so it's 0.085 molar in sodium butanate. The butanoate is the conjugate base of butanoic acid. And what will happen from there? Well, first off, let's just go ahead and calculate the percent ionization of part A. And if you recall, Ka looks like this. This is the generic form of Ka, and this is saying the non-dissociated acid, well, that is your reactant, and here's the products on top, which is your H plus and your conjugate base, the A minus. This is the generic form, and we're given the butanoic acid right here, which is undissociated. That would be the term that goes there, and what goes up here if you do your ICE, but if you just remember that it's going to be equal to, since there's nothing else in there, it's going to look like this: x squared over the concentration of the undissociated acids. We can solve for Ka in terms of x squared, and so we have x is equal to, if we solve this out, the square root of Ka times the undissociated acid's concentration. If we plug in the numbers that we have, which is 1.5 times 10 to the minus fifth for our Ka and our 0.0075 for our molarity, it would be like this. It would look like this, which is the concentration of H plus is the square root of the Ka times the concentration of the undissociated acid. And this, of course, is going to equal our H plus, and that gives me 3.35 times 10 to the minus fourth, and that's equal to our H plus concentration. Percent ionization we can get from this. The percent ionization is our H plus over our undissociated acid. So percent will equal 3.35 times 10 to the minus fourth all over 0.0075 times 100, since it's percent, and you put that in your calculator and you get 4.47% ionization. Now what we want to know is, if we take that same solution that's 4.47% ionization and we add enough sodium butanoate to bring it to that entire solution to 0.085 molar sodium butanate, what's going to happen? Well, we'll use our ICE method on that, and so that's initial, change, and final. And so let's just go ahead and put our concentrations down. Butanoic acid, our H plus concentration, and our conjugate base, which is the butanoate. Initial concentration of butanoic acid is 0.0075 molar. It's 0 for the H plus concentration, and butanoate is 0.085 molar. That's our initial. Our change is going to be minus x, because the butanoic acid is going to dissociate a little bit. Therefore, since it's monoprotic, we're going to pick up an x, and we're also going to pick up the same amount in moles for our butanoate conjugate base. And our final, let's just add them up. And we're going to assume, since this Ka is pretty small at 10 to the minus 5, that these x terms can be safely dismissed. So we'll dismiss these two right here. And so we can write out our final form as being like this, which is the Ka 1.5 times 10 to the minus fifth is equal to our products, which would be X times 0.085 molar divided by our reactant, which of course is our butanoic acid. We're just writing out the Ka form, 0.0075, and we go ahead and solve for X, and X is going to be equal to, we're going to bring this around, brought this from the bottom, we brought it up, and then we're going to bring this term down below, and we put that in our calculator, and we got 1.5 exponent 5 minus times 0.0075 divided by 0.085 equals, and I get 1.3 2 times 10 to the minus 1, 2, 3, 4, 5, 6 times 10 to the minus 6. And to get our percent ionization, we're going to take this, which is the H plus concentration of our example B, which contained our additional common ion, and that's going to be 1.32 times 10 to the minus 6th over our original concentration of undissociated acid, which if you remember is 0.075 molar butanoic, and that's times 100, and we get, let's see, we're going to divide that by 0.0075 and then multiply times 100, and we get as our final answer 0.018% dissociated. Now this is an interesting result. The butanoic acid, without anything else in there, if we just throw it into a solution of 0.0075, we'll get around 4.5% dissociation. But if we add a fairly substantial, about 10 times, 0.08 versus 0.0075, about 10 times, we add about 10 times of the common ion in there, we go from around 4.5% to practically not being dissociated at all. This is 0.018%, a very small number of dissociation. So the common ion effect is pretty powerful on the percent dissociation.